Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 5. We're going to talk today about second order linear ordinary differential equations. To motivate this, let's consider an object hanging by a spring having a certain mass. There could be a number of different forces acting on this spring, on this object. The total force may involve, first of all, the force of the spring, in addition to that, we could have force of resistance. And furthermore, we could have some fan blowing here at variable speed. We could add an arbitrary force to the mix. Analyzing this equation, forces are masses times accelerations. We'll write that as m times the second order derivative of y with respect to t. If y is the displacement of this object, making this go from here down to here, that will be, according to Hooke's law, negatively proportional to the displacement itself. The resistance should be proportional to the velocity, but it goes in the opposite direction of the velocity, and that's why it's minus b dy dt. If y is increasing, then the force of resistance should be in the opposite direction. It should be in the negative direction. Finally, the arbitrary force at the end can be any function of t at all. Rearranging the terms in the equation that we have for modeling a spring, we have m d squared y dt squared plus b dy dt plus ky equals f of x. We say that this is a second order linear constant coefficient ordinary differential equation. If there is no forcing function over here, we might also add the adjective that this is homogeneous. But if the forcing function is not identically zero, then it is non-homogeneous. Adding all of these adjectives might seem frightening to begin with, but don't let it fool you. The more adjectives you have, the smaller the class of differential equations that you're working with, the easier it will be to solve them. We are going to focus on differential equations in this form. And initially, we're going to focus on the homogeneous case. Before we get too far into the development of the theory, I would like to look at some simple examples. First, using Newton's notation for dots for each derivative with respect to time, I want to consider a simple harmonic oscillator. In this case, we have a mass, we have a spring force, but there's no resistance and there is no external force function either. I claim that any function of the form c1 cosine the square root of k over mt plus times the sine of the square root of k over mt is a solution. To check this claim, we need to calculate the second order derivative. The first order derivative will be minus c1 square root of k over m sine root k over mt plus c2 square root k over m cosine root k over mt. The second order derivative will be minus c1 k over m. You get another factor of the square root of k over m by the chain rule, cosine root k over mt, and then minus c2 k over m sine root k over mt. Notice that this is negative k over m times the original hypothesized function y. It follows that my double dot plus ky will be m times minus k over my plus ky. The m's cancel and we end up with 0, which demonstrates that the claim was true. It follows from work that we did in the last video that the solution to simple harmonic operator problems is going to be a function of the form a cosine root k over mt minus some phi naught. In other words, the solution to the simple harmonic oscillator problem will always be some kind of sinusoidal function with some amplitude, phase shift, and period. I want to look at another example. In the next example, suppose that we're dealing with an oscillator that has some spring constant equal to 2, but also a coefficient of friction equal to 2. I claim that y equals e to the minus t cosine t is a solution. To check this, we need to calculate a couple derivatives and then plug those into the differential equation. To calculate the first order derivative, we need to use the product rule. The derivative of the first times the second plus the derivative of the second times the first to take the second order derivative, we need to apply the product rule twice. Derivative of the first here gives us e to the minus t cosine t. Derivative of the cosine part gives us plus e to the minus t sine t. When we take the derivative here of the e to the negative t, we'll get another plus. So I should get 2 of those terms. And then when I take the derivative of the sine part, I'll get a cosine, so that's minus e to the minus t cosine of t. This term will exactly cancel this term. Plugging all of this into the differential equation, we have 2 e to the minus t sine t plus twice negative e to the minus t cosine t minus e to the negative t sine t plus twice e to the negative t cosine t. Here you can see that when we distribute this 2 here, this term will exactly cancel this term. And when we distribute here, this term will exactly cancel this term giving us a grand total of 0, and that completes the proof of the claim. Note that if our solution to the problem with friction is e to the minus t cosine t, we get oscillation, but the amplitude of those oscillations decays exponentially. Not linearly, not quadratically, but there's an exponential decay in the amplitude of the oscillations. Back to our second order linear, constant, coefficient, homogeneous. I'm going to assume that the solution has the form e to the lambda x, where lambda is assumed to be some possibly complex number. If that's the case, then y prime is going to be lambda e to the lambda x, and y double prime is lambda squared e to the lambda x. Substituting all of this into the differential equation, we get 0 equals a times lambda squared e to the lambda x plus b times lambda e to the lambda x plus c e to the lambda x. We have three terms, each of which has a common factor of e to the lambda x. We could factor that out and obtain a lambda squared plus b lambda plus c. Now all of this equals 0, and by the zero product theorem we have the following. By the way, if you don't remember the zero product theorem states that if you have two things multiplied together that equal 0, then either the first factor is 0 or the second factor is 0. This first factor can't be 0, and that implies that the second factor must be 0 for this equation to be true. We see that in order to have a solution of the form e to the lambda x, we must have a lambda squared plus b lambda plus c equals 0. We're going to call this the characteristic equation. There are only up to two distinct solutions to the characteristic equation, and we just can say more about what those solutions look like by applying the quadratic formula. Lambda has to be minus b plus or minus square root b squared minus 4ac all over 2a. In our theory, we're going to assume that a, b, and c are real numbers. However, there's a principle about real numbers called trichotomy. Every real number is either positive, negative, or 0. That leads to three cases with respect to these second-order linear constant coefficient homogeneous ordinary differential equations. Under the radical, b squared minus 4ac can take one of three possibilities. One, it can be positive. If the b squared minus 4ac is positive, then we get two real distinct lambdas. The second possibility is that b squared minus 4ac is 0. And if b squared minus 4ac is 0, then you get one real solution, but it appears with multiplicity twice, multiplicity 2, in the characteristic equation. The third possibility is that you get a negative value under the radical. In that case, you get two complex conjugate solutions. In case 1, you have two solutions, e to the lambda 1x and e to the lambda 2x. These are both solutions. Are combinations of these also solutions? We need to investigate that. First, some terminology. A linear combination of functions y1, y2, up to maybe some yk, is an expression c1, y1 plus c2, y2 plus ck, yk for constants c1, c2 through ck. Now, a theorem. The theorem states that any linear combination of solutions to a homogeneous linear equation is also a solution. Let me state that more particularly. If y1, y2 through yk solve a linear equation, that is homogeneous, then any linear combination is also a solution. The proof is fairly straightforward. You just plug the linear combination into the differential equation and rearrange the terms and see what happens. So we'll have c1, y1, ck, yk, the nth order derivative, all the way down to the constant, well, the 0th derivative term. We'll rearrange the terms, which we can do. This gives c1 a(n) of x, y1 superscript n, a0 of x, y1, and then we can combine these as well. ck a(n) of x, nth derivative of yk, a0 of x, yk. Now we're assuming that each of these y's is a solution. So when you plug it into the differential equation, since the differential equation is homogeneous, this has to be 0. Similarly, all of these other terms are equal to 0, and the whole thing equals 0. That's the end of the proof. Let's work an example. Let's look at y double prime plus 5y prime plus 6y equals 0. The characteristic equation is lambda squared plus 5 lambda plus 6 equals 0. We can solve this by factoring. Lambda plus 2, lambda plus 3. The solutions are minus 2 and 3 at minus 3. This gives us two solutions. y1 is e to the minus 2x, and y2 is e to the minus 3x. But more than that, the theorem tells us that any linear combination of these is also a solution. So c1 e to the negative 2x plus c2 e to the minus 3x gives me a two-parameter family of solutions. Now, we expect, because this is a second-order equation, that to undo two derivatives, we get two integrals, and hence two constants of integration. So we expect there to be a two-parameter family of solutions. We have not proved that this represents all possible solutions in this family, but we're getting there. Before developing more of the theory, I'd like to give an example where we have an initial value problem. Suppose I have y double prime plus y minus y prime minus 2y equals 0. Y of 0 equals 2. Y prime of 0 equals minus 1. This represents an initial displacement of 2 and initial velocity of minus 1. The characteristic equation, by the way, this is a very strange spring if it represents a spring, since the spring constant is negative. So the more you displace it, the more it wants to be displaced. That would be a very strange spring indeed, but we can set up mathematical models that don't represent anything in reality. The characteristic equation is lambda squared plus lambda minus 2 equals 0. We can factor, this is lambda plus 2, lambda minus 1. That'll give us the 2 lambda, and a minus lambda gives you 1 lambda here, so that lambda is minus 2 or 1. This gives us two solutions, and in particular, it gives us a two-parameter family of solutions, c1 e to the minus 2x plus c2 e to the 1x. To account for the initial data, we need to calculate the derivative, which I'll do right here. The derivative is minus 2c1 e to the negative 2x plus c2 e to the x. Now, we plug in x equals 0 to the original function, we should get y equals 2. That gives us c1, plugging in 0 here, we'll have c1 plus c2 equals 2. One equation and two unknowns. We need one more equation to determine the constants c1 and c2. This second initial condition, we'll plug in x equals 0 and obtain negative 2c1 plus c2 equals minus 1. This system is very simple to solve by subtracting. c1 minus negative 2c1 is 3c1. c2 minus c2 cancels. And 2 minus negative 1 is 3. From this we deduce that c1 is 1. Based upon the first equation, if c1 is 1, then c2 is also 1. That means that the solution to the initial value problem is y equals e to the negative 2x plus e to the x. Before proceeding, I want to give you a little bit of notation. An upside down capital A is the logical quantifier for all. A backwards E stands for there exists, and an exclamation mark is a symbol for uniqueness. I can state the following theorem. For any A, B, C, y naught and y naught prime that are real numbers, there exists a unique solution to the initial value problem ay double prime plus by prime plus cy equals 0, y of x naught equals y naught, y prime of x naught equals y naught prime. The proof of existence will be by explicit construction. The uniqueness part will be proved later. To continue with the development of our theory, we need a definition. We say that the functions y1, y2 through yk are linearly dependent on an interval I if there are constants c1, c2 through ck, not all 0, such that c1 y1 of x plus c2 y2 of x plus ck yk of x is identically 0, and that means for all x within the interval I. That's what it means to be linearly dependent on the interval I. I want to point something out. You can always choose the constant c1 through ck to be equal to 0 and get the expression to have a linear combination that is identically 0 for all x on any interval. The trick is to find constants where they are not all 0. In that case, if, say, c1 is not 0, that means that the function y1 can be expressed as a combination of the other functions by simply moving these functions to the other side and dividing c1 off. It is as though if y1 can be expressed in terms of the others, y1 is not giving new information. We may as well throw it out from our collection of functions, and we can reconstruct, by simple linear combinations, the exact same set of functions. Our goal is to try to construct all solutions to our linear homogeneous problems using linear combinations of the smallest number of functions possible. To express this idea about the smallest number of functions possible, we need to know the term linearly independent. We know what it means to be dependent, and if functions are dependent, then one of those might be expressed in terms of the others. To be linearly independent means the following. We say that y1, y2 through yk are linearly independent on some interval I if whenever you get an expression that is a linear combination of these, that's equal to 0 for all x on I, the only way that can happen is if all of these constants are 0. Another way of saying this is that our functions are linearly independent if and only if they are not linearly dependent. I should mention that if C1, C2, and CK are all 0, that trivially gives you a linear combination that gives 0. We call that the trivial combination. For example, show that the functions y1, which is equal to, let's say, cosine of 2x, y2 equals cosine squared of x, and y3, which is identically equal to 1, that these functions are linearly dependent on the entire line. To do this, all we need to do is find a linear combination of these functions that gives you 0. We can do that because of the half-angle identity. Cosine squared x is 1/2 1 plus cosine of 2x. We can distribute this and then move this term to the other side to get 0 is 1/2 times 1 plus 1/2 times the cosine of 2x plus -1 times the cosine squared of x. You can see now that we have a non-trivial linear combination that gives us 0. These functions are linearly dependent. Also, you can see from this identity that cosine squared of x can be expressed in terms of a linear combination of the other two. It's as though from the function that's identically 1 and from cosine 2x, you can already construct all of the information encoded in cosine squared x. Let me give you another example. Suppose y1 is e to the x and y2 is e to the 2x. Show that these are linearly independent. To do that, we need to show that the only solutions C1 and C2, so that this equation holds for all x, will be when C1 and C2 are identically 0. Now, if this holds for all x, it has to hold for any x that we choose. In particular, I can set x equal to 0, and it must still hold. And if x equals 0, we get C1 plus C2 is equal to 0. We can also see what happens if we plug in x equals 1. If x equals 1, we get 0 equals C1 times e plus C2 times e squared. This gives us a system of two equations in two unknowns. We should be able to solve for both of the unknowns, C1 and C2. Note that we can divide the second equation by e. We'll have this system, C1 plus C2 equals 0, but also 0 equals C1 plus C2 times e. If we now, let's see, we'll multiply the top equation by -1 and the bottom equation by 1 and add. We'll have 0 equals, the C1s will cancel, and we'll have two terms involving C2. We'll have C2e minus C2. We can factor the C2 out and apply the zero product theorem. The only way the product of two factors can equal 0 is if either the first factor is 0 or if the second factor is 0. The second factor is not 0, and so we deduce that C2 is 0. But from the first equation, if C2 is 0, that implies that C1 is 0, and that means the only linear combination that gives you 0 for all x is the one where both constants C1 and C2 are 0. That means that these functions are linearly independent. A triangle with 3 dots like this means therefore. Let's do one more example. Let's look at y1 equals cosine of x, y2 equals sine of x. Are these linearly dependent or are they linearly independent? We'll form an arbitrary linear combination and assume that this holds for all x. If it holds for all x, it has to hold for any x that we choose. Suppose we choose x equals 0. The sine of 0 is 0. The cosine of 0 is 1. So when x equals 0, we get c1 of 0. But it has to hold for other values of x that we choose too. Suppose we choose x equals pi over 2. The cosine of pi over 2 is 0, while the sine of pi over 2 is 1. And hence c2 is also 0. Since both c1 and c2 are 0, we deduce that these functions are linearly independent. Okay, it may be difficult at times to determine whether or not some given collection of functions is linearly independent or linearly dependent. We need a simple check. And so we're going to develop kind of a silver bullet way of determining whether or not a collection of functions is linearly dependent or linearly independent. We're going to start with this equation. And I'm going to go all the way to the subscript n, from C1 through Cn. If this equation holds for all x, then it will certainly hold, especially if these are solutions to an nth order differential equation. This should hold when I take the derivative as well. I started out with one equation in n unknowns, C1 through Cn. I now have two equations in n unknowns. But if I have n different unknowns, it takes n equations to specify those unknowns. This is the zeroth derivative equation, the first derivative equation. We need to keep going. We need to keep going until we get to the n minus first derivative. If we go from 0 to n minus 1, this will give us n equations. We have n equations in n unknowns. A theory from linear algebra tells us that a system like this of n equations in n unknowns has a unique solution if and only if the determinant of the coefficient matrix is not 0. The coefficient matrix will consist of the functions y1 through yn, their derivatives and second derivatives all the way down to the n minus first derivatives. Remember, the variables here, the unknowns, are c1 through cn. So these functions are their coefficients. I'm going to define the Wronskian of these functions y1, y2 through yn at some point x naught. Well, it is denoted by w of y1, y2 through yn, and then this will be a function of x. I'm going to evaluate that at x naught. And it's defined by, sometimes I'll suppress the functional dependence upon these functions here, or vice versa, might just suppress the functional dependence on x. The idea is that we need this to be the determinant of these functions evaluated at x naught, the derivatives evaluated at x naught, all the way down to the n minus first derivatives evaluated at x naught. Let's look at an example. Suppose that y1 is e to the x, y2 is e to the 2x. Then the Wronskian will be the determinant where we plug these functions into the first row, and in the second row we put their derivatives. To calculate the determinant, we multiply this way, and then we subtract the product the other way. So we get 2. When we multiply, we add the exponents, e to the 3x, and then we subtract the product this way, e to the 3x. What we get is e to the 3x. Note that what we get is not 0 for any x. It follows that the one solution to a linear combination of these equal to 0 is that with coefficients c1 through c1 and c2 equal to 0, which means these functions are linearly independent. As another example, when y1 is cosine x and y2 is sine x, and just a point of advice, do cosine first. And that way the Wronskian will end up being positive instead of negative. The derivative of cosine is negative sine of x, and the derivative of sine is cosine of x. When we multiply this way, we get cosine of squared of x, but we have to subtract the product this way. When you subtract the negative, you get a positive, and what we end up with is identically 1, and in particular, never 0. Since the Wronskian is never 0, we deduce that these functions are linearly independent. For another simple example, let's suppose y1 is x plus 1, y2 is x minus 1, and y3 is 1. The Wronskian is calculated by plugging these functions into the first row. The determinant can only be calculated for a square matrix, so you need to calculate the derivative and then the second derivative. Since one row of this determinant is all zeros, the Wronskian will be identically 0, and that means these functions are linearly dependent. But you can see that because if I take the average of x plus 1 minus x minus 1, I get 1. That tells me that the third function, y3, can be expressed as a linear combination of the other two, so they are obviously linearly dependent. I'd like to state something called Abel's lemma. And it goes like this. If y1 and y2 solve ay double prime plus by prime plus cy equals 0, where I'm assuming that the coefficient a is not 0, so this is a bona fide second order linear constant coefficient homogeneous ordinary differential equation, then either the Wronskian is identically 0, which means that if it's 0 at one location, it will be 0 at all locations in an interval, or the Wronskian will have this form: a constant c times e to the minus b divided by ax, where c is constant. One thing that Abel's lemma tells us is that if the Wronskian is not 0 for some x, then it won't be 0 for any x. If it's not 0 at some particular x, then this constant can't be 0. And if the constant's not 0 and the exponential function is certainly never 0, then the Wronskian will never be 0. So either the Wronskian is identically 0 all the way across the interval, or the Wronskian is never 0 across the interval. To prove Abel's lemma, let's look at the Wronskian. The Wronskian is the determinant of y1, y2, y1 prime, y2 prime. I'm proving this for second order equations, but we could prove this just as easily for nth order equations. This is y1, y2 prime minus y2, y1 prime. What is the derivative of the Wronskian? The derivative of the Wronskian can be calculated by the product rule. It's y1 prime, y2 prime, plus y1, y2 double prime. That's the derivative of the first term. Minus y2 prime, y1 prime, plus y2, y1 double prime. We can see right now that this term cancels with this one. In what is left over, we have to keep in mind that y1 and y2 are assumed to be solutions to our second order linear constant coefficient homogeneous ordinary differential equation. It follows then that y2 can be expressed as minus b y2 prime minus c y2 divided by a, because it satisfies the equation a y2 double prime plus b y2 prime plus c y2 equals 0. We can move these terms to the other side, making their coefficients negative, and then divide the a off. We get a similar expression over here, which we apply to y1. It's going to be minus b y1 prime minus c y1 divided by a. We have a common denominator of a, but we do get some cancellation. When we distribute y1 over here to the second term, we get negative c y1 y2. When we distribute negative y2 here to the second term, we'll get positive c y1 y2, which means that these exactly cancel against each other. What's left has a minus b over a here and a minus b over a here. I can factor out minus b over a. What's left is y1 times y2 prime minus y2 times y1 prime. But this is the Wronskian. We have the derivative of the Wronskian is negative b over a times the Wronskian. This is a separable first-order equation for the Wronskian. We see that the Wronskian satisfies the differential equation dw dx is minus b over a times w. If we separate the variables, we can write that as 1 over w dw equals minus b over a dx that we can then integrate. On the left, we get the log of the absolute value of w, and on the right, negative b over ax plus c. Solving for w, we exponentiate both sides and obtain w is a constant times e to the negative b over ax, and that completes the proof of Abel's lemma. We should probably state as an explicit corollary that if y1 and y2 solve our second-order linear constant coefficient homogeneous ordinary differential equation, and if the Wronskian is equal to 0 for some t hat, then the Wronskian is identically 0. If the Wronskian is not 0 for some t hat, then the Wronskian is not 0 for all t within the interval of solution. For this particular differential equation, the solutions with the equations having constant coefficients, the interval of solution is the entire set of real numbers. To be really explicit, let me mention another corollary. If we have some solutions to our basic problem, and if the Wronskian is 0 for some t hat, then y1 and y2 are linearly dependent. If the Wronskian is not 0 for some t hat, then y1 and y2 are linearly independent. So the Wronskian is an easy test for either linear dependence or linear independence.